Hello, my name is Cavalcanti. I'm a professor at the Department of Computer Science, and I'm here with Professor Ian Ferland from the Department of Chemistry. We both would like to tell you about our Center for Doctoral Training. It's called Albert and is concerned with autonomous robotic systems for laboratory experiments. Albert is an initiative of YorRobots. This is the network of researchers at the University of York interested in robotics. York research in this area is across at least 9 departments and 1 school, covering total 11 disciplines. So multidisciplinarity is a unique feature of research in York in the area of robotics. It caters for areas like computer science, engineering, and in the case of Albert, chemistry, all the way to archaeology, psychology, sociology, and others, covering all aspects of the development of a robotic system for use in our society, in chemistry laboratories, in other forms of laboratories, but also working in many other areas, public areas, interacting with humans. So robotics at York covers multiple aspects of the design and verification to develop mobile and autonomous robots that are advanced, ethical, safe, trusted, reliable, and certifiable. These will be features of the Albert robots. To achieve these properties, multidisciplinarity is key, and Albert offers projects in all these areas of research represented in York. YorRobots is part of the Institute for Safe Autonomy. Here on the right, you have pictures of our brand new building, which is a flagship initiative at the University of York, to provide support for us to develop autonomous systems, their software, and their communications in a way that ensures that they are safe. Albert robots will be provably safe. We have in the Institute for Safe Autonomy an ecosystem of interdisciplinary collaboration, and YorRobots and Albert are at the heart of those collaborations. The students working in Albert will be part of the Institute's community. Research in the Institute is organized in 4 pillars, covering design and verification, assurance, communications, society, and ethics. Under design and verification, we are interested in developing and testing safe-centered software and hardware, and that's where Albert is inserted. Albert research will be concerned with safety, as I have mentioned. The facilities of the Institute make it a living lab. We have state-of-the-art spaces for testing and developing new applications, and the Albert students will have access to those facilities as needed, and will collaborate as part of this very rich, very positive research environment. I will now pass on to my colleague Ian Ferland, who will tell you more about the research mission that we have in Albert. Thank you.
Thank you, Anna. My name's Ian Ferland from the Chemistry Department, and I'm Professor of Organic Chemistry here at the University of York. I'm delighted to be able to tell you a little bit more about our plans to automate and incorporate, you may say, robotic systems into our labs. And this is to accelerate the way that we do our experiments, but also to think about how we might make our molecules for a whole raft of applications in a very much safer and controlled manner. And so to do that, we need to bring together, as Anna has already said, a whole range of different expertise and experience from across the university. The Albert project involves a team of different people with complementary interdisciplinary expertise. You have myself from chemistry and also Anna Cavalcanti from computer science, who are the directors. We also have project coordinators, particularly Pedro Ribeiro, who's playing a lead role on the coordination of the Centre for Doctoral Training, as well as John Oiken from computer science, who's allowing us to facilitate interactions with industry and commercial partners, and Charlotte Willans from chemistry, who's going to provide expertise, experience in the training of our students going forwards. In terms of the funding for this particular project, that mainly comes from the EPSRC, University of York, but also industry partners as well. And that comes to around about £1 million worth of funding. The lead team also involves colleagues from law, other colleagues from computer science, psychology, sociology, physics, electronics, as well as archaeology. And we expect other departments to get involved with this project going forward as well. The vision for the CDT itself is to come up with autonomous robotic systems for laboratory experiments. And we have the tagline, cleaner, greener, cheaper and safer. So this is where we're thinking about utilizing robotic systems on a much bigger scale in our laboratories going forwards. And whilst the focus will be predominantly on chemistry laboratories in the first instance, we anticipate that we'll see the roboticization of other types of labs across the university. So if we can think of physics, we can think of the environment department, biology department, wider areas which would very much benefit from robotic systems. One of the big chemistry grand challenges is to be able to synthesize any compound on demand. And you may not know so much about chemical synthesis, but this is a big area that requires urgent attention. So we need molecules for all sorts of different things, not least in our pharmaceuticals, our therapeutics, but also in our agrochemicals, pesticides, insecticides, herbicides, the very thing that are critical to food security and avoiding famine around the world, but also advanced materials. The latest, what's going to be the next compound that is required to illuminate your screen, or a material that needs to have some sort of biological, medicinal properties that protects you from harmful microbes, bacteria, viruses, and so on. We're wanting to also transform chemistry, and of course there is thinking about how we improve developing drugs, agrochemicals, and the novel materials. And we are talking an area that's really critical to society. And onto the Albert vision. We're very much interested in using robotic systems to sort of take on the roles that a typical lab technician might be involved with. And we're still very much keen to involve humans, but perhaps we can do that in a different way and think about how might we exploit human-robot interactions in the laboratory to really elevate the types of work that we can do in the lab. And so we're very much keen to entertain projects where we think about those human-robot interactions. We can think about applications, as I said in the last slide, wider labs, not just chemistry, but also different areas across the University of York. We're looking for adaptable robots. We want robots that can do different types of things. And of course, dexterity and precision are absolutely critical. We want those robots to be able to interact with humans and human equipment. And equipment is critical to many labs, particularly chemistry labs, where there's lots of different types of equipment, but also sensitive compounds and materials that require control and precision in how these robots might interact. Of course, we also need robotic systems that are trustworthy. And there's a focus here on safe, secure and resilient. As Anna has pointed out in her slides, it's this really critical and builds on the Institute for Safe Autonomy and thinking about how we would use these robotic systems to really embed a safety culture within chemistry laboratories and wider labs as well. Of course, we want to address grand challenges, and that would be fit for different areas of application. And we're keen to do impactful research and make connections to industry as well. And in industry, what we've seen over the last 10-15 years is very much a situation where robots are being really taken on board in laboratory settings, and we're seeing specialist units as well as robotic systems being used in general lab settings as well. So if you're interested in one of the projects or the general vision for the Albert CDT, I very much encourage you to click on this link here, and this will provide you with an outline of the projects that have been put forward by colleagues from across the university. We've asked that projects are proposed from academic supervisors that involve at least 2 different departments, and this is really critical to really embed this idea that we really want to take advantage of interdisciplinarity. In terms of contact, you can email us. You can email the team directly on this email here, and very much encourage you to do that. You can also contact any of the members of the lead team, and we'd be very happy to chat with you, either by a Zoom call or in person, if you would prefer that, or even by email as well. So please come and talk to us and see what PhD project might be available for you. Thank you.
Now we'll hear about the experience of studying for a PhD at York from Holly and Barney. Please, would you like to share your screens or go ahead?
I don't have any slides. I'm just happy to talk about my experience. So I'm currently in my 3rd year of my PhD as part of the RoboStar research group. I'm doing interdisciplinary work, so I'm part of both. I have computer science and psychology as part of my research. And I came into my PhD from industry. So the close ties that YorRobots has with industry was really helpful for me to kind of assimilate and change into this new academic research route that I'm doing. So that's been really interesting and really helpful for me. I have kind of changed my career route and want to become a lecturer. So a lot of what the university offers and the department has allowed me to get experience in that. So I work as a graduate teaching assistant and can teach students individually, do some prep work, do some lecture development, and it's all been really helpful on that front. And the university also has multiple schemes. So at the moment, I'm working through one that's helping me get my Associate Fellowship in Higher Education Award. That's been really useful for my own personal development. In terms of the more social sides of doing a PhD at the University of York and the computer science department in particular for me, I'm part of the PhD committee, and we're putting together activities, both academic and social, to try and bring PhD students together and to get to know each other and to spend more time outside of our research, but creating a community. So I've had a really good experience so far as part of computer science and part of the University of York as a whole.
Thank you very much, Holly, for sharing your experience. That's very pleasant to hear about your change from industry to academia. Barney, would you like to share your experience with us as well?
Yeah, I'll share my screen.
Okay.
So I'm going to talk a bit about my project, just because I think it's a good indicator of my experience so far at the university. So my project is on data analysis of cross-coupling reactions, enhanced mathematical understanding of complexity and the development of a self-optimization robotic system for high-throughput experiments. So I did my undergrad at this university, and I moved from the maths department to the chemistry department, and it's been a bit of a culture shock because the chemistry department is, I've gone from doing maths to being thrown at the deep end with the chemistry. So far, it's been really good. The chemistry department is amazing. It's full of wonderful people. It's got some amazing equipment. Our lab has 2 robotic systems. Has the Chem Speed, which is sort of a Fume HUD with all your different chemistry equipment in it, and robotic system, and it does like batch experiments, so it can do like 72 experiments, I think, at once. And we also have this other one called powder dose equipment, which essentially is a simultaneous and automatic dispensing of different powders into various vials, and it goes down to sub-milligram level. And that is another way we'll be able to get the batch going quicker. My role in this is I'm going to be utilizing the mathematical element of my expertise. And we'll be using methods such as principal component analysis, hierarchical clustering, heat maps, to extract as much information as we can from the data, so that then we can optimize the experiments. And the overall outline of my project is to manually assess high throughput reaction data for cross-coupling reactions. This is things like Suzuki reaction, which is one of the most widely used reactions globally. And then we'll then move on to automating the data analysis side, and then eventually develop a self-optimization algorithm, so that we can try to connect the results of the automated analysis to provide instructions for the next set of experiments. And in doing that, I'm going to get full training on robotic systems down in Basel in Switzerland, which will be really exciting. And then finally, we're going to assess the impact of the automated reaction routes, which I think is in collaboration with the Sociology department. And then finally, the current work I'm working on is I'm analyzing a data set from Pfizer using high throughput experiments. And this is using Suzuki. And this is just a couple of different types of outputs that we get, so you can get a general overview of what I'm doing. In regards to my experience so far at the university, it's been wonderful. The chemistry department has made me feel very welcome, and I definitely am thinking more about where this can lead me in the future. I think doing a PhD is going to open up so many different avenues for me, and it's really exciting that I'm getting to work with robots. It's such a cool PhD. Thank you.
Thank you very much, Barney, for sharing your experiences, also talking about your work very much in the context of what Albert is about. So we have time. Yeah.
Do I have time to ask a question?
Yes, absolutely. We do have. I was just about to say that.
Oh, right. Thank you very much. Thank you both for sharing your experience. I think one point that prospective applicants might worry about is the way in which they will need to work across different departments in most cases. So, Barney, perhaps it's early days for you, but I wonder if you already had some experience of how this is managed. And I know that Holly has some experience of working across two departments with supervisors coming from two departments. So if you could both say something about how you see that, it would be very useful thing. I think it would be very useful for prospective applicants. Thank you.
Will I go first?
Okay, you went first.
Okay. So as I said, my research is with computer science and psychology. So I have a supervisor both in computer science and in psychology. I also have an external supervisor because I'm doing a studentship that's funded by industry. So I actually have 3 in total. So I have a meeting every week with my supervisors, and I share meeting notes post those meetings so that any of my 3 supervisors that can't attend will still get a full update as to what's going on and any discussions that we've had. And that's been really useful to keep up to date and to get input from people that can't make it to a specific meeting but can read those notes afterwards and provide their own thoughts and any extra advice that might have been useful during that particular meeting. I've not really had any issues when it comes to trying to communicate between my supervisors. So it's been really useful. It's also quite helpful because if one's busy, I can normally turn to the other. So there's always somebody around. And because my work is multidisciplinary, I can talk specifically to somebody who has the knowledge and experience in a particular area of the work that I'm doing. And then we can discuss that as a group, but we've got that specialist knowledge and experience there available to talk about. So that's been really, really helpful for me.
Thank you, Holly.
Yeah, in a similar vein, I have, I think, 4 supervisors. I've got 2 in the chemistry department, one in the maths department and one in the sociology department. I've yet to meet my supervisor in the sociology department. My lead supervisor thinks, wants me to get settled in first, and he's sort of giving me a bit of breathing room. In the same way, I haven't formally met one of my other chemistry ones. I have a weekly meeting with my math supervisor and my chemistry supervisor. Sort of, we all get together and we talk about what we're doing, where my project's going. Sort of, it's good because I get like my data analysis side comes from the maths department, so I get lots of input from Jess, my supervisor, whereas Ian gives me a lot of input on why certain things are the way they are in a reaction. Sometimes I find things where I think that must be wrong, but then Ian reassures me that no, maybe a certain type of reactant they've used is the reason why. We also have a monthly report that we send out, and I send mine to all my supervisors, which I think is a good way for them to keep tabs on what I'm doing, even if I have yet to meet them or haven't spoke to them this month. Mm-hmm. Yeah, it's really good. The whole interactions we have when we're all together, it's really like informative, and like sometimes we chats and I find out something that I didn't even think of. So very good, and they offer lots of support. So
okay, thank you very much, both of you. I think I would like to reassure the prospective applicants of Albert that they will have a setup that's similar to what you just described, even though the work will be multidisciplinary, but the students will be associated with a particular department. They will be carrying out a PhD in a particular department. That department will take a lead in terms of admission and also throughout the experience of the student as a PhD throughout the PhD. And in that case, you always have very clear guidance of what you need to do and having the benefit of the extra expertise. So I think that's to reassure applicants. Thank you very much, both of you. Thanks, Pedro.
Thank you, everyone. So I think we can move on to the first project presentation, and that's Simos, please.
Right, good. Let me see if I can manage to share the screen. So good afternoon, everyone. Thanks for organizing this great event. And let me see if I can desktop. Here we are. Okay. So first of all, Barney, you must be the PhD student with the most number of supervisors, and it's good to but taking this opportunity, it's good to know that it's my pleasure to be here today and learning more about the multidisciplinary work that is being done and the project that's being done within Albert. So it's on my side, it's my pleasure to introduce this exciting PhD project, which is entitled Domain-Specific Languages for Collaborative Human-Robot Laboratory Experiments. As all the projects here are funded by York, University of York and the Albert CDT. So this PhD project is jointly supervised by Professor Dimitris Kolovos and myself. I'm associate professor or senior lecturer at the Department of Computer Science, and targets the development and evaluation of domain-specific languages that can support the design and execution of collaborative human-robot laboratory experiments. So similarly to how Barney described of he's collaborating using robots to carry out the experiments. In a similar way, we try to abstract or use domain-specific languages to define how the human and the robot will collaborate in order to undertake these laboratory experiments. And you can find more information by following the URL at the bottom right, or by scanning the QR code. So robots, as we very well know, robots are increasingly used in several application domains in order to support labor-intensive and complex tasks, including infrastructure inspection and maintenance, delivery of medical supplies within healthcare facilities. Following the same motivation, the same intensive, robots are also used within model laboratories, and they typically work alongside scientists or technicians in order to execute long-running scientific experiments. For instance, the KUKA robot on the right is currently being deployed in a particular laboratory environment. And once it is programmed and provided with a particular plan that it needs to execute, it can operate for about 21 hours every day per day. So the workflow that this mobile robot performs includes, among other steps, of sample preparation and analysis, which essentially could be done much faster than the manual methods or semi-automated methods, which may not be non-autonomous. So essentially, by leveraging these repeated tasks to robots, scientists, they can devote more time and more effort to focus on the most challenging parts of their workflow that cannot be typically undertaken by a robot. But despite its benefits, designing and executing these workflows and the experiments is complex, time-consuming, and error-prone. So the challenge in this particular case mainly arises because the sequence of operations underpinning the collaboration between robots and scientists should be explicit and easily understood, but also they can be modified when needed. Also, current approaches that involve designing ad hoc solutions are typically based on handwritten protocols, spreadsheets, and custom software, which is difficult to understand, communicate, maintain, and share. So this particular PhD project addresses these challenges by leveraging the power of domain-specific languages, which in conjunction with model-driven engineering principles helps domain experts to specify experimental designs via specialized and intuitive languages. So more specifically, DSLs can help scientists to specify the details of an experiment and its workflow. And for instance, the equipment, the procedures, the measurements in a structured and formal way that can be validated, simulated, and executed using widely used robotic simulators such as Gazebo and ROS. Furthermore, by using model-driven engineering, DSLs can support the experiment design and analysis, including visualization, optimization, and verification. So the overall project objectives include, first, the investigation of the various types of DSLs, for instance, graphical, textual, and their combination, that would be more suitable for the specification of scientific experiments where human experts and robots collaborate seamlessly within a laboratory environment. Secondly, to study how DSLs can be integrated with existing experimental design and execution workflows and processes to support the execution of those workflows. And finally, to assess the effectiveness and efficiency in terms of various key performance indicators, for instance, productivity, reproducibility, and maintainability that is offered by these DSLs when used for scientific experiment design and execution over the traditional approaches that are currently being used. Now, the overall approach of this PhD follows the normal steps of a PhD at the University of York, and in particular, it has the following steps. First, that is the review of the literature on DSL engineering and human-robot collaboration. Secondly, becoming familiar with state-of-the-art technologies for DSL development and model-driven engineering, which are the foundation of the overall PhD. Then conducting interviews and surveys with domain experts, scientists, and laboratory technicians, also other PhD students who have expertise in laboratory experiments in order to gather requirements and feedback on the use of domain-specific languages for experiment design and execution. Then design and implement DSLs for targeting this set of experiments, the design, their execution based on the identified requirements and best practices. And finally, integrate the domain-specific languages within existing experiment design and execution processes and platforms, and evaluate their effectiveness and efficiency through case studies, experiments, and using feedback from scientists and laboratory technicians. So if you want to find out more about this PhD, feel free to follow the URL of the QR code at the bottom right. And also feel free to reach out to Dimitris or myself if you have any questions. Thank you.
Thank you, Simos. Move on to the next project. Charlotte, please.
Thank you, Pedro. Just share my screen. Hopefully you can see that. Shout out if you can't. So the project that we're advertising uses robotics to remove the harmful effects of toxic metals in industrially relevant processes, and it's supervised by myself, colleagues in chemistry, Ian Fairlamb, and also physics, Lawrence Wilson. Oh. Apologies. See if I can. Okay, can you still see the screen okay? Brilliant. So many metal catalyzed processes are used in industrial processes. So homogeneous metal catalysts have a lot of advantages. They're highly selective, they can be highly active, they can use mild conditions. And most pharmaceutical processes have several of these metal catalyzed steps. There are challenges with using metals in industrial processes. One of the major ones, that's my pointer, one of the major ones is the separation of these metals downstream. And this is one of the challenges that this project aims to address. So within our group, we've already developed an automated flow platform, and this is for the high throughput synthesis and screening of metal catalysts. And it uses an electrochemical approach to making our metal complexes, which is a relatively unusual way of making them. So we have libraries of ligand precursors, which are added to our electrochemical reactor. And when they come into contact with a cathode, that ligand precursor is reduced to form a ligand which can now coordinate to a metal complex. Within our electrochemical reactor, we have a sacrificial metal anode. This oxidizes and releases metal ions into solution. And then in solution, these two come together to form our metal complex, which can then go on to form a catalytic reaction. So this is a nice sustainable way of making these metal complexes. And this is just an example of one of the reactions that we might do inside the reactor to make this type of metal complex that can then be used in catalysis. So most metal catalyzed processes used in industry rely on precious metals. These are at risk of dwindling supply and rising costs. And it would be really nice to move towards base metals in these processes, such as nickel, which are much more abundant. The next step is a catalytic reactor. So because in the electrochemical step, the only byproduct is hydrogen, which bubbles off, we don't actually have to isolate and purify a metal catalyst. We can telescope it directly from the electrochemical reactor into the catalysis reactor. And this is just an example of the type of reaction that we might develop inside that catalysis reactor. So this is a Suzuki reaction, which again, it's a reaction that's used very widely in industry. Although base metals are more preferable to use in these processes, there are challenges with them. So in the case of nickel, whilst our metal plate, our nickel plate that we use in this reactor is non-toxic, the actual catalyst that we form in that reactor is highly toxic. And there are problems with handling this in a safe way. So the idea of this project is to incorporate another automated step within our flow platform, which is an electrochemical recovery step. So here we are generating our metal catalyst by oxidizing the metal complex. We use it in the catalysis reactor, and then we'd like to reduce the metal back into an electrochemical step, which we can then recover and reuse in our electrochemical reactor. So as I've already said, one of the challenges with using metals in processes is that they're difficult to separate downstream, which means that they cannot be reused. This means that it's costly, both from a monetary point of view, but from an environmental point of view as well. Thinking about the mining of these metals, the transportation, the use, where they end up downstream, and then issues with toxic contamination. So what this project will do is develop an automated electrochemical recovery step within our flow platform. It means that the metal can be reused. So this electrochemical reactor simply goes back to the beginning and it's reused again. This will significantly reduce the cost of those metals. It can be done locally. So once the metal is brought in, it can be used over and over again on site. And also it has a much lower environmental impact because these metals are not being washed away and into various systems. And because this is a closed loop system, there's also a safer handling of these metals. So we start with nickel as the metal plate. We use it in this step here, but it doesn't have to be handled until it's reduced back onto the electrode, where again it's safe to handle and then can be recirculated back around into that step there. So that's a summary of our project. As previously, if there are any questions, do feel free to email me, or I'm happy to take any questions depending on time.
Thank you very much, Charlotte. I think a bit short in time, so I'd like to move on to the next project, and it's Anna, please.
Thank you very much, Pedro. I will share my screen now. Again. Oh. Hello again. The project that I'm putting forward is a project to be co-supervisor by myself and the other co-director of Albert, Ian Felland, and it's concerning robotic chemist for fume cupboards. So the computer scientists that might be interested in this project may not know what a fume cupboard is. I'm sure the chemists that may be interested in the project will know. But here's a picture of a fume cupboard. There are several in our chemistry department, and they are used in a range of experiments. An issue with these fume cupboards, not shown here in the picture, is that they can cause physical strain on the chemists that are using them. Basically, they have to stand in front of such a cupboard with their hands inside it, protected by a physical separation, normally inside some gloves. And it is a very difficult position to maintain for a very long time. So it limits the amount of time a human operator can manage. And it would be very interesting to be able to share that task with robots. However, trustworthiness of such robots is required for several reasons. First of all, the robot will be in a lab surrounded by humans. The robot will be dealing with dangerous chemicals potentially, and in any case should avoid waste of time and materials and so on. So there are several properties of interest that we should establish before we decide to deploy such a robot. But the general question is, can we trust a robot? The question is similar. If we ask, can I trust my autonomous vehicle? Can I trust my all the automation that is in modern cars or in planes and so on? There are all sorts of techniques that you should use in several aspects, and we are concerned in particular with software engineering, with the development of the programs. And basically what we want is to use engineering techniques, not hacking, not sit down, try to write the code and see what happens via ad hoc testing experiments. So I am part of RoboStar, which is a center of excellence on software engineering for robotics, which says, like just every engineer, we start developing models. But we are going to be dealing with these very advanced features of the Albert robots, adaptation being one of them, and going to provide support to use of techniques that are traditionally of interest for roboticists, like testing via simulation, for example, but also more modern applications where you can actually say more than we can do via testing, by saying we consider all possible ways in which a particular task can be carried out, and I know that there are no problems here. The scope of the project is very open. It will be of interest to students interested in the foundations of software engineering, but also to students that are interested in the development of tools, the development of robots, the development of these particular applications and their evaluation, for instance, in the chemistry laboratory. The initial proposal for the work plan is that the student will start with a study of the state of the art, looking at existing robots and the approach that have been used to develop these robots. What evidence do we have of the behavior of these robots? Then we'll think about how can we create a better robot, the brain of a better robot that's adaptive to a class of experiments, can deal with fume cupboards arranged in a different way, and also can deal with the situation where the cupboard changes. A human came along and then changed something, and the robot goes back and finds something changed. So we will be considering how to model these problems and then add value, perhaps generating tests automatically or generating simulations automatically, and then running these tests either in the field with deployment or with the simulations that were automatically generated. So this is the overall idea for the project. I'm very much welcome questions, but I can be reached via my website, and I'll be very delighted to have a discussion and provide more details about the project. Thank you very much.
Thank you, Anna. I'd like that we move to the next project presentation with Darren, please.
Hello, hello. Let me just share my screen. Great. Hello, everyone. My name is Darren Reed from the Sociology department, and the project that I would be supervising alongside Jim Woodcock and Ian Fairlamb is an ethnographic study of the chemistry laboratory. Now, I suppose this is slightly different from many of the other projects, but in many ways it underpins those other projects. So the logic here is that we want to contribute to the overarching program of work within the Albert CDT. And to understand that, we want to kind of broadly sketch in the motivations, the objectives, and the reach. So if we want to develop the science, engineering, and socio-technology that underpins the building of a laboratory-based robotic system, we have to understand the spaces in which those systems might be used, the people that might use them, the practices they might use them for. In the sense that these systems are meant to have a positive social outcome, they are also based on the idea that they are more efficient and that they bring certain advantages in terms of kind of cleaner and greener and safer. This implicates people in that process, the manner in which they use them, and their understanding of those technologies. The great thing about the Albert CDT is that, of course, it brings people from many different departments, and I've put sociology and right at the end of that list modestly, but it also includes law. So when we think of a laboratory, we tend to think of a nice clean space, a very organized space. And when we think of robots in that space, this is the kind of imagery that we tend to think about. It's all very there are no humans in that video. It's also quite unmessy. And so in reality, the laboratory space is full of human stuff, human behaviors, and also mess in many ways. The use of these technologies, therefore, is a very human practice. I love the idea of human mess, the idea that humans actually get this stuff done. We are perhaps messy creatures, yeah, maybe in an organized way. If we were to introduce technologies like robots into these spaces, we have to understand how those spaces are currently used, how they're navigated, how people move through them, how things like safety is understood, and also how that messy space is a productive space. So, put more formally, this ethnography will research the everyday practices of those in the chemistry laboratory. It will identify mundane relationships between human practices, laboratory space, and technical devices. The manner in which these devices integrate into those practices might well be seen as assistive or automated. But there's a difference between those two things. Obviously, assistive technologies are going to help with help a human do stuff perhaps more efficiently, or automated processes are likely to replace those humans. Understanding how the technologies in the future will fit into the laboratory, then it's to understand what current practices are like and how those rely on assistive devices and systems, and what parts of those practices are automated. The notion of the socio-technical is a very sociological idea, but essentially it relates to humans and technologies together. And together they undermine notions of safety, and this occurs or is regulated within those particular spaces. We might talk about material logistics and all the organizational relationships, which in some senses help coordinate, regulate, constrain those spaces and what can be done in them. The understanding of all that kind of messy human stuff is meant to be productive, not only in terms of the sociology and understanding how people work within the laboratory, but the manner in which new technologies might be introduced into those processes to support them, automate them, replace them, and those kinds of things. So therefore, this ethnography is highly integrated with all the other projects in the sense that they might underpin the development of particular kinds of technologies. And one of the aspects, one of the outcomes is a set of design requirements based upon the manner in which those spaces are currently being used. The project would suit a sociologist with ethnographic or qualitative research experience, but also perhaps someone from human-computer interaction who has done this kind of ethnographic work, especially those who have worked within a technology development for particular locations and spaces. The analysis of human conduct and interaction is also as an aspect of this. Not all sociologists have that. The manner in which technologies are interacted with or interacted through would be a useful set of skills. Perhaps a familiarization with what's called science and technology studies within sociology, which is this socio-technical approach to understanding people and machines. And also there's a very strong link to the project in law, which I co-supervise, which is concerned with regulation and safety of these spaces. You can find out more information about this project by contacting me, and I'm sure there's a link to the Albert website, which will give more information. That's me. Thank you very much.
Thank you very much, Darren. In the interest of time, we'll move to the next project presentation. Arvind, please.
Hello, everyone. So this is the law project, but it's a joint project between law and sociology, and will be co-supervised along with Darren. As a lawyer, I haven't done slides, but I'll be talking you through what the project involves and why it might be of interest to someone. So, as you know, Albert is about creating a robot for use in the chemistry lab, which will be cleaner, greener, safer, and cheaper than conventional techniques, and will open up new avenues for research. But getting that right requires strong legal input from a creative, curious, interdisciplinary legal scholar. The project we have in mind for law will be an interdisciplinary, theoretical, and empirical exploration of the everyday world of regulation, and particularly the question of our high-level policies and regulatory frameworks become part of everyday practices. When we think of regulation, we tend to think in terms of the rules, the words, the ideas that are there in legal texts. But if regulation is to succeed, those words, ideas, and rules need to be embedded in what scientists who are actually working in the infinitely complex world of an actual functioning chemistry lab, what those scientists actually do. And what the law project is about bridging that gap between the legal world of the regulators and the experiential practice-based world of the scientists in which this robot is going to be embedded. You will look at how people working in scientific contexts navigate the mesh of rules applicable to them. You'll examine the relationship between the scientific mission, the organizational culture of the lab, and the world of law and regulation that seeks to govern and shape the practice. And perhaps most interestingly, you will explore what implications this has, not just for how we write rules, but how we design a robot that works in a chemistry lab that is aware of and synchronized with human practices. What are we looking for in terms of your background? We need someone whose background is in law or regulation and who has an interest in the interface between law on the one hand and science, technology, and robotics on the other. We need someone who has an understanding of how regulation is transformed by and translated into the world of everyday practice. And we're looking for someone who has an interest in and the ability to take on a project that looks at how regulation should work in this exciting new world where human action is ever more intertwined with autonomous systems and autonomous robots. So what the project will be doing is looking at how we can design robots to be aware of and responsive to legal norms and to the ways in which humans think and work with ideas of safety and responsibility. That, in a nutshell, is what the project will be about and what the work you will do will be about. Please feel to get in touch with me if you have any questions.
Thank you very much, Arvind, for your presentation. We'll move on to the next project by Barney. Manish, please.
Sorry, I didn't realize I was on mute. Can I share my screen?
Absolutely.
Okay, just a second. Are you able to see my screen?
Yes.
Yeah, so this project is about a robotic two-dimensional infrared spectroscopy for biomolecular fingerprinting of cancer. So if you try to understand what really it involves basically two interdisciplinary techniques. One is coming from the photonic side, which is infrared spectroscopy, and then we are talking about integrating it with robotics. So just to give you a brief outlook, like what are we looking at? So we're saying that we want to explore infrared spectroscopy for analyzing any biological samples, for characterizing their features and understanding the structure of them for relating it with cancerous growth. So it's two-dimensional infrared spectroscopy is actually a new variant which has promised to offer new unique analytical technique for characterizing complex biomolecular samples. And generally what happens is the bond between the atoms is in the molecular structures, they absorb this infrared light at specific wavelength, and the infrared spectrum provides valuable information on the functional groups, on the chemical composition, and the molecular structure of compounds. So in this spectroscopy method, we would like to measure the two-dimensional molecular fingerprinting, which will give a unique molecular structure and allow to get the sensitive information of the protein structure. And how does it help to analyze cancer? So the moment you have the protein structure, you will know what's happening inside the cancerous tissues, how is the mineralization happening, why is it having less of oxygen, and so many other biological growths which are happening around it. But now, how does robotics help you? So with robotic automation, we would like to get the fingerprinting of the protein, lipids, and nucleic acids, all the biological fluids, and this will help in cancer detection and characterization, which is a very important part of analyzing any cancerous growth, whether it's stomach cancer or lung cancer or even which is on rise right now is breast cancer, even prostate cancer. So what happens is we collect liquid biopsies and we will analyze it through the infrared and two-dimensional spectroscopy. At the moment, we have got an entire new setup in the laboratory which can measure the two-dimensional infrared spectroscopy, but the sample preparation takes a lot of time. And that's where we would like to introduce the robotic version of the infrared spectroscopy. The end effects of this project will actually lead you to develop an entire platform for basically treating or analyzing any kind of cancerous samples or any kind of biofluids, which will help in monitoring the effect of cancer treatment. So preparation, measurements of protein samples in combination with candidate drug molecules, and it will help in facilitate high throughput screening and structural impacts of drugs binding to the proteins. So as an effect of this, the ideal candidate who will be participating in this project will be trained to work with robotic systems. Introduction to AI and machine learning algorithms will be given to them so that they can utilize those algorithms to analyze the spectrum of the infrared spectroscopy. The ideal candidate for this project will be somebody who has decent amount of introduction to the chemistry. Even if it's less introduction to the robotic side, it's perfectly fine. We can train the student on that area. At least a basic understanding of machine learning will be ideal. So I would like to stop here and say thanks to you. If you have any questions, please feel free to get in touch with me. I'll provide you more details. And I think the details of this will be on the website of Albert CDT.
Thank you very much, Manish. We'll move on to the next stall. Mahmoud, please.
So, hi everyone. So let me just share my screen. All right. So good afternoon. So can you see my screen? Yeah.
We can, yes.
Perfect. So good afternoon, everyone. So this is another exciting project under the Albert CDT. So this project is titled Autonomous Robotic Systems for Solar PV Material Synthesis and Quality Control. So the main supervisor of this project is myself. I'm Mahmoud Dhimish, and I'm assistant professor in electrical engineering at School of Physics, Engineering and Technology. And this project also will be co-supervised by Professor Miles, who is the director of the Institute of Self-Autonomy, and Richard, who is a reader in chemistry from the Department of Chemistry. So mainly the aim of this project is to advance solar cells chemical synthesis for fabrication of new solar cells. So the biggest aim is just really to create and fabricate new solar cells. This will be achieved by integrated autonomous robotic systems in the fabrication process, and also advanced artificial intelligence-based algorithms for decision-making and optimization of the new solar cells materials and also the efficiency. So this project also aims to use advanced inspection methods for quality control of the new solar cells that we are aiming to fabricate. So for example, we will utilize electroluminescence and photoluminescence imaging techniques in order to check the reliability and durability of these new fabricated solar cells. So this is a really new, exciting area of research that is ongoing and growing in the UK and worldwide, whereas we adapt AI to actually optimize the materials and the chemical reactions and synthesis in the solar cells. Now, in order to achieve this, so we have set up really 4 different objectives. for the project. So first, we will start the project by developing a suitable, let's say, autonomous robotic system for solar cell material synthesis. And it's really important here to note that when discussing chemical synthesis in the context of solar panels, so we're talking about the fabrication and compositioning of semiconducting materials and components utilized in the panel actual construction, rather than just the photophysical process that is responsible from the conversion light to electricity. So that's really the biggest kind of aim, or the first biggest aim of the project. But the second objective is then to integrate sensors within the new fabricated cells. So aiming to collect data on the solar cell efficiency, but also to enhance the chemical synthesis and fabrication process to make it very fast and robust. So the sensors will be integrated, or the sensors integrated in the process will be immensely useful to achieve the third objective of this project, whereby we look to create an AI-driven approach, decision-making algorithms that are capable of identifying the best material to use in the fabrication of these new solar cells. So also the AI algorithms will identify the problems in the fabrication process, for example, cracks in the cells that they might occur during the fabrication and manufacturing the panels. And therefore, the AI algorithm will help to improve the actual cell efficiency and reduce any issues really related to the cell reliability, durability, and degradation models. So the last objective of this project is to apply safety and ethical consideration when it comes to the implementation of the first kind of three objectives. So for example, we can just look at we need to make sure that we apply ethical approach when it comes to advancing and developing these AI algorithms, as well as the data integrity unit that should be embedded within the sensors development. So as I said before, so the project is set to have a new materials characterization, so which we can actually implement at the University of York in our UKRI Strategic Equipment Fund, which is what we call atomic layer depositioning system, where we can deposit new materials and test them and fabricate them on the solar cells. And also we have the electro and photoluminescent imaging systems, where we can actually characterize the cells, trying to make sure that there is no reliability and degradation of the panels, as well as we can look at the efficiency of the generated or the samples that we generated through this research. So this project is not only lab-based project, so we have to make sure that it is kind of have an industry impact. So we will apply our methods in industrial settings. So the project will benefit from collaborating with Above Surveying Ltd, which is a leading UK-based company in the solar cells fabrication and digitization. This is really particularly useful to achieve the first two objectives of the project. So the implementation of the AI algorithms, so for example, to achieve objective 3 and to achieve the objective of creating and optimizing the process of the manufacturing and solar cells efficiency, we will not really start from scratch building these machine learning and deep learning models. So we will collaborate with Google DeepMind to use their existing pre-trained machine and deep learning models, and therefore we could speed up the execution of the projects and obviously the impact, the industrial impact of the project. So that's kind of the whole project objectives and streamline. Again, thank you very much for attending this session, and please get in touch with me, Mahmoud, Dhimish, if you have any further questions related to this project.
Thank you, Mahmoud, for the presentation. Move on to the next project. Chris, please.
Okay, can you hear me okay?
Yes, we can.
Right, I'm just going to attempt to share my screen and then make this presentation full screen. That may or may not work. Can you see that okay?
We can see your screen. It's not full screen, but we can see it.
Yeah. Well, rather than faff about with this to try and make it full screen for the full 3 minutes, I think I'll just start, if that's okay, in the interest of time. So my project is in a kind of similar vein to the previous two, in the sense that it's about how do we automate the process of scientific discovery, and how do we optimize new novel physics, in this case, to do interesting applications. So specifically, it's about automation of high power laser experiments. I'm Professor Christopher Ridgers from the School of Physics, Engineering and Technology, and I'm collaborating on this project with Dr. Stephen Wright from the Computer Science Department and Chris Aaron, who's also from the School of PET. Okay, if I just scroll down. So just to kind of orientate you, when I talk about high power lasers, I'm talking about very high power lasers. So typically we can make lasers with a power of 10 petawatts, a petawatt is 10 to the 15 watts. So that's a 1 with 16 zeros after it. And to give you some context, it's as if we took all of the sunlight on the surface of the Earth and focused it onto a grain of pollen. We get to that kind of intensity that we can reach with these lasers. Now, you can probably imagine that that allows us to reach some quite extreme conditions. In particular, we make plasmas. So whenever these lasers are incident on any matter, they ionize it really quickly, and they can accelerate the charged particles in that plasma to very high energies over very short distances. So typically millimeters as opposed to kilometers in conventional accelerators. So one application of these high power lasers is as a compact particle accelerator for kind of fundamental physics, but also for medical therapies as well. So we can also accelerate ions. So here's a picture of a simulation of ion acceleration. And we can use those ions perhaps for proton therapy, and we could maybe make smaller, more compact machines and make it cheaper. You may have seen in the news that recently we use lasers to create the conditions for controlled fusion. And so another application of high power lasers is to make a fusion power plant. Now, these are all really interesting and nice, but there's one big problem, and that's that typically our experiments on with these lasers have been limited to perhaps 1 or 2 shots a day, maybe at best a shot every minute, but no faster than that. If we're going to realize these applications, we need to do these things at 10 to 100 times a second. And this, I should have said at the beginning, this project is also in collaboration with the Central Laser Facility at the Rutherford Appleton Lab, and they have pioneered a new kind of laser technology where we can do high power laser experiments at 100 hertz. The problem is, at the moment, we don't really know how to do that. In particular, we need to automate these experiments if we're going to best use them to discover the kind of interesting physics that goes on here. And that's what this project is about. This project is about how do we build robots, robotic control of these high power laser experiments to realize these applications. So this project specifically is going to be to design and build a robotic target control system that will allow us to then completely automate these experiments. This will be coupled to, oops, I'm trying to scroll here, I don't know if this is working. That will then be coupled to a machine learning Bayesian optimization loop that we have developed, which can be used to optimize the experiment for whatever application it is we want. In this case, it will be particle acceleration. We then use that optimization loop to kind of hone in on interesting parameter regimes that wouldn't have been apparent to us without this algorithm. We can learn lots of new interesting physics this way. Yeah, there we go. We're going to use this to explore the physics. Prerequisites: a degree in physics, engineering, or an equivalent discipline is essential. And as part of this project, you will gain some skills in control engineering, high performance computing, team working on these kind of large scale experimental facilities, work in a range of environments because you'll be working in academia, but also collaborating with national laboratory and our industrial partners on this. And I hope you could see my slides okay. That's me done. Thank you.
Thank you very much, Chris. I'd like to move on to the next talk then, please, Jihong.
Yeah, sure. Just let me share my screens. Can you see?
Yes, we can see it. Yeah.
Yeah, okay. So my name is Jihong. So I'm a lecturer in robotics at School of Pet. So my project is on a robot chemist that can learn from humans. So you will basically supervised by myself and also Professor Andy Terrell at PET and also Professor Ian Phelan at Chemistry. So the aim of this project is to automating shell-like lines operation with robotics and machine learning. So this is a typical shell-like line when I took the picture at Professor Ian Phelan's lab. So to kind of operate on this this complex system, you need it's a really repetitive task, and we hope, of course, to automate this process by using vision and tactile sensing. And by the way, this shell-like line is present in many of the chemistry lab around the world. So the student will be based on Robotic Systems Living Laboratory at the Institute for Safe Autonomy and have access to some of the most advanced robotic systems. So I'm just going to show the student what you expect. So this is the robotic system. So it is controlled by torque control. So you can see that it's behaved like mass spring damper system, and you can actually adjust the stiffness. So you can basically adjust in the stiffness in any directions, where if you can tune stiffness all to 0, then you can actually move it around. And even not only in translation, but you can also do it in rotation as well, as you can see here. So it is a redundant manipulator, so it has extra degrees of freedom, meaning that you can actually maintain the same pose or move the joint around. We also implement a teleoperating system where you can actually teleoperate the robot, and in this case, to trying to teleoperate it to grasp a cube and put it elsewhere. So you will be able to see. So these are something you would expect. So this is our robotic system. In the previous slide, I just show what a Schöner Glide look like. We are going to use this kind of robot to operate in that system. Also, we are going to use not only vision, but tactile sensing. So you can see here, this is the state-of-the-art geosite sensor, where you can actually feel the thing that you touched. So this is our really advanced system that we already have this available, so the student can use to conduct their experiment with the robot, and also the real chemist in the real chemistry settings. So what we're going to investigate is something called imitation learning, where the robot is programmed by imitating the human behavior instead of required explicit programming. So here is one of the example of imitation learning. So you can actually, instead of program the motion, now you are able to demonstrate the motion to the robot, as you can see here. Then the robot in this process collect data, and then it perform on its own a different kind of task. So you can see, actually, this is a really different situation than the previous one, but the robot is programmed by imitation learning, so you don't have to explicitly program this motion. The robot can still do the task. So this is basically what we're gonna use to try to program the robot to operate the Schöner Glide, as I shown in the first figure. So, I mean, that's basically about the project. If you have any questions regarding the project, you can contact me at Jihong Zhu. So if you have any questions, feel free to drop me an email. All right.
Thank you very much, Jihong. I'd like to move to the next project. Cade McCall, please.
Okay, can you hear me?
Yes, we can.
Okay. Okay, so the project that I'm supervising is modeling human supervision of autonomous systems for chemistry labs. So I'm supervising this with Anna Cavalcanti from computer science and Jason Lynam from chemistry. So this is a psychology-focused PhD. So what we'll do is we'll use experiments to test the ways in which the introduction of autonomous systems into the lab might change the way that humans think and make decisions about their research. So discovery research it requires what we call complex decision making. You're all the time dealing with uncertainty. You're trying to decide what's the best next experiment to run, what are your key questions, what are your key variables, what are your key manipulations, and etc. So there are a lot of unknowns here. That's what makes it research. And that's what makes that decision-making complex decision-making. And complex decision-making is interesting in psychology because there are all sorts of cognitive mechanisms that go into deciding under uncertainty. And so the key question with this PhD is looking at how the introduction of autonomous systems to the complex decision-making in labs might change the way in which people deploy different cognitive mechanisms to make those complex decisions. So the work in this PhD will be around running experiments to look at this, to look at how the introduction of autonomous systems changes complex decision-making. And we'll do that with empirical experiments based on simulations. So mainly there'll be simulations using VR or other kinds of sort of digital simulations where we manipulate the presence or absence of an autonomous system in a laboratory environment. And then what we're going to look at is how people make decisions over time. So there are a variety of tools in psychology that allow you to take someone's behavior in a simulation and then use cognitive modeling and computational modeling specifically to derive different parameters about their behavior. So how much do people explore their environments or explore their different options? How much do they learn from trial and error? What level of risk taking do they engage in? And how good are they at balancing short-term losses with long-term gains? So these are the kind of parameters that we can derive computationally from people's behavior, and we want to do this in the context of human autonomous system interactions to look at things like, does the delegation of work to autonomous systems change the way people explore their options? Do they take greater risks? Do they learn as well from trial and error, and etc. So like I say, the approach will be running experiments using virtual reality or other digital simulations, and then we will use computational modeling to derive parameters of human behavior, and we'll test the effects of autonomous systems on these different features, these different cognitive processes that go into complex decision making. So that's the project.
Thank you very much, Cade. I'd like to move to the next project. Stuart, please.
Can you hear me, and can you see my slides?
Yes, both. Thank you.
Brilliant. Okay, so what I'd like to introduce is a project that is looking at a kind of holistic all-lab view. So we have this sense of robots being able to aid us and autonomy being able to give us useful insights in the laboratory. But there's also this kind of bigger issue of the integration of many different systems. And so what this project will be looking at is how you can do that in a very practical, low-cost way to achieve really interesting results. So the challenge is that I'm going to argue is that in order to kind of take advantage of automation and take advantage of it truly, is we need to kind of glue all these different things together. But the real problem is, especially in kind of academic research environments and kind of chemistry laboratories and so on, is that there's this huge diversity of equipment and experiments and users and, quite frankly, funding. So bringing all of those components together in a meaningful way is really challenging. And how do you adapt that system for every different lab so that you can kind of make a system or make a solution that's applicable to lots? Now, the opportunity that you'll be looking at in this project is to take advantage of some existing very cost-effective open source systems that have been developed in the last few years and trying to apply them to the laboratory environment, because these systems have actually been created in the home automation sense, kind of smart home sense. But actually a lot of the techniques and the tools are really applicable to the research laboratory as well. So the project itself is looking at studying the needs of interdisciplinary laboratories. So my lab is very interdisciplinary. The co-Is on this project, Dr. Chris Spicer and Professor Alison Parkin, are also big interdisciplinary labs. We do lots of different kinds of experiments. And so a big part of that is a user study. How do you actually do this? What will actually be useful to those environments? The second part is developing the kind of open hardware that's needed to talk to all of these tools. So that's taking advantage of existing frameworks that do things like these little, you can't really see it with a blur, but ESP32 microcontrollers, little systems that can run embedded code and that have the kind of GPIO pins that can talk to different systems. But it's also about how we then integrate it with existing open source software. So rather than just kind of saying you should build this from scratch, I'm saying start with some existing open source frameworks, things such as Home Assistant, which is the most contributed project on GitHub. Huge project, huge amounts of open source effort. And looking at how we can adapt that to different systems and using existing protocols such as MQTT or even automation frameworks such as Node-RED. Real practical tools that be the basis for your work. Develop it into some guidance and then promote and publish those things and look at opportunity exploring it. So for you, this project would be interesting if you're an open source advocate, if you like working with microcontrollers and hardware, and you're also excited by the idea of developing a really practical solution that can apply to lots of areas. It's a very new research group. You won't find much about me online, so reach out if you're interested. But we're studying bioelectricity and bioelectronics. There'll be lots of robotic problems around interface design, and it's a very highly interdisciplinary team. I want to stress that we focus a lot on research culture and your real personal development. So come and talk to me about it if you're interested. There are the details if you want to find out more.
Fantastic. Thank you very much, Stuart. I'd like to move to the next presentation, and that's Jason, please.
Trying to find how to stop the screen sharing because it's disappeared off my screen.
Thanks, Stuart.
Thanks.
Oh,
still there? Here we go.
Can you see and hear me okay?
Yes.
Presentation, great. Thank you. Thanks very much. And thank you for the opportunity to talk today a little bit about our project. So this is a joint project between myself and Ian Fell. I'm in the Department of Chemistry, and Jessica Hargreaves in the Department of Mathematics. And there's a very long title, but what we're interested in doing is to develop new and automated ways to acquire spectroscopic data, and then also to develop methods to do in-depth data analysis so that we can discover new chemical reaction pathways and new catalysts. Because really what the key challenge that we have is trying to develop and understand chemical catalysis. As you can see on this slide, it's a vitally important thing for the UK economy, and it contributes, it's estimated, about £50 billion per year to the UK. And therefore, having the best catalyst for your reaction is really, really important. And what we've been focusing over the past few years is trying to understand, if you take this, for example, this hypothetical chemical reaction here, A plus B making a new product, trying to understand all of the different steps that lead us to actually making the product. What are the individual steps that the catalyst takes? Because if we understand that, what we can do is then design the best catalyst. And the approach that we've used over the past few years is based on a method called infrared spectroscopy, which allows us to interrogate the bonds within molecules and give us information about it. And what we've done previously, as shown on the left-hand side here, is use ultra-fast laser systems so that we can actually look at the individual bond formation steps that underpin catalysis on timescales ranging from picoseconds to milliseconds. And in complementary studies, what we've also done is have a look, for example, about how the catalyst decomposes. Because understanding how your catalyst dies is really important in terms of developing the next generation. Now, these are really, really what we would view anyway, really important results and insights into chemical catalysis. But there's a huge problem with it, and that's performing those sort of reactions, those sort of studies is an incredibly time-consuming process from both a user perspective, but also from actually performing the experiments, but also from doing the data analysis as well. And so what this project is all about is to try and develop automated methods to circumvent all of those issues. And in the first instance, what we've developed is a system which is called the AirMax, and our prototype system is shown here on the slide, which is going to enable us to do those sort of measurements, but in an automated fashion. What we're trying to develop is a system where we'll have an array of different samples, which can then be automatically fed into the spectrometer systems that we have, both here in York and also where we collaborate at the Central Laser Facility, so that instead of manually preparing individual samples in a what is a laborious and time-consuming fashion, we can actually perform these experiments in a much more rapid and a much more controlled manner, hopefully one day from the comfort of our offices. And then tied in with that, much of the data analysis is done in a very traditional fashion, and that is we simply eyeball the data, we look for trends, we then try and do some fitting and modeling. And we believe that the data sets that we get that contain many millions of data points, we're not really analyzing them to the full potential. And so again, developing automated methods to interrogate the data, to try and understand what's going on, and so we can get much more detailed insight into these chemical processes, a vital part of this project. And by merging these two things together, what we hope to get is both automated data analysis and automated data acquisition. So what would a student doing this project be involved with? So what they would be involved in is development of automated data collection methods starting with our prototype system and then building it on so that we can do more and more data, more and more complicated sampling using spectrometer systems here in York. We'd also look to develop new methods to probe the data in more than that sort of relatively simple method that we do at the moment, and then use these to develop self-learning systems so that actually the reaction can optimize itself towards a given product. And we will provide training in things like laboratory automation, programming, state-of-the-art spectroscopy, and also design of experiments and data convolution and analysis. Hopefully give a complete picture of how to do modern spectroscopy in an automated fashion. Thank you.
Thank you very much, Jason. I'd like to move to the next talk, and that is Babar, please.
Hello, can you hear me?
Yes, we can.
Hi, my name is Babar Jamil, and I am the primary supervisor for this project on inherently safe extensible robotic system for laboratory process automation. This project is part of CTT program at the University of York, and the co-supervisor for this project is going to be Dr. Pedro from the Department of Computer Science. Now, I believe Albert is going to complement some of the terminologies that are used in Industry 4.0, and this specific project will look into process automation through robotics while ensuring the safety of both machines and the humans. Now, robotics in the laboratory is not a new concept, and in fact, there are a lot of laboratories doing extensive research on using robotics to automate different chemical processes, such as the case of this video that is showing the process going on in the University of Liverpool. Now, these videos show a lot of robot processes, but the lacking thing here is we don't see complex scenarios in which robots are required to handle some complex task. When we talk about complex tasks, we can assume these automation labs, such as the case in these ChemSpeed automation labs for chemistry experiments. And often we require to move microtiter plates, which has the samples processed by these machines, and move them from one machine to another machine. This is often a very careful and critical task for chemists in the lab experiments. Now, for a conventional robot to handle samples from these machines is going to be a very tough challenge, because it requires the robot to care for the safety of the machine, and also requires the robot to have capabilities that are not yet been discovered. So this project is going to try to make a novel robotic arm that has the ability to extend its arm and move or navigate in these machines and do pick and place tasks from one machine to another machine. This will, in fact, will automate some of the processes that are going in the chemistry labs that requires extreme care. So the critical challenges are the task of this project are going to be development of extensible robotic module that is going to be integrated with a robotic arm. This robotic module will be simulated first using the simulation software for virtual experimentation. And we would like to discover the mathematical modeling and control of this whole integrated system. And in the end of the project, we would like to deploy the simulations onto an actual robotic system that has the ability to have pick and place tasks. We will also like to integrate some of the features into this robotic system, such as integrating the remote access and fully autonomous control. The requirements for this project are that you must possess a desire to work on a challenging topic. Other important requirements for this project are skills in programming such as C++, Python, ROS, or any related languages to robotics. You are also required to have the understanding of mathematical modeling of the dynamical systems, and it is expected that you have basic understanding and experience in CAD software such as Inventor or SolidWorks, and any other experience such as physics simulation software is a plus point for this project. We also expect you to have the basic understanding of control theory, such as applied or theoretical. the student is going to get a lot of training necessary for doing this project, such as the case of going to laboratory and learn about the experiments going on to these going in these labs. The student will also receive intensive training to improve the specific skills required for this project. And we will also allow the student to have graduate level modules courses to improve the specific skills to advance their understanding on this project. If you have any queries or questions regarding this project, please do not hesitate to contact me or the co-supervisor on this project. And for any information, please scan the QR codes to either get more information or apply for this project. Thank you very much.
Thank you very much, Babar. I'll move to the next project. It's Xinwei, please.
Yeah, hello, can you hear me?
We can hear you and see you, yeah.
Yeah, sorry, I didn't prepare a slide, but I will quickly introduce our project. So I'm Xinwei Fang, a lecturer in computer science, together with Dr. Jihong Zhu, a lecturer in robotics from the School of Physics, Engineering and Technology. We're leading this PhD project focused on enhancing situational awareness in robotics for chemistry laboratory experiments. So one of the major challenges for physical robots deployed in real laboratory settings is that they will often encounter the degradation of physical components or the changes in their operating environment. Due to the limitation of the sensor deployment, such changes are often unmonitored, creating a pathway for those changes to impact the performance of the system. So this PhD project aims to address this issue by proposing a novel framework that can identify, detect, and reason about changes that often goes unmonitored. This work will focus on modeling the behavior of the system in a stochastic model and identifying changes in comparison to their expected behavior. The evaluation will be conducted in a simulator as well as a real robotic arm. This project offers an exciting opportunity for those who are passionate about making tangible impact in the world of AI and robotics, particularly in enhancing the safety and efficiency of laboratory experiments. Thank you.
Okay, thank you very much, Xinwei. We'll move on to the next talk presentation by Professor Radu Călinescu and Helen Snedden, and this is actually going to be a recorded video because I could not attend. So just bear me with a second so I can share the presentation.
Hi, I'm Helen Snedden, and I'd like to introduce the Albert PhD on the synthesis of green and safe chemical reaction networks, prioritising sustainability. I work in the University of York Green Chemistry Centre of Excellence, having moved there last year from industry, and I've spent years looking at the design of processes and the selection of reagents, solvents, and reaction parameters, trying to optimise the sustainability of synthetic chemistry reactions. And so I'm really excited by the possibilities offered by Albert to harness the power of high-throughput, autonomous, continuous flow robotics to address one of the key challenges in all of this, getting enough data in an efficient and timely fashion to be confident that we're making sensible recommendations. And I'm even more excited that for this particular PhD, I'll be partnering with Radu Călinescu, who sadly can't be here for this presentation, because Radu, from the Computer Science Department, brings the skills in mathematical modelling of chemical reaction networks to ensure that we'll have confidence in our findings for this particular PhD. The project will involve picking some key synthetic processes of industrial interest and synthesizing chemical reaction networks, not in the lab, but computationally, using continuous time Markov chains and/or ordinary differential equations. We will then annotate fragments of these networks with any specific safety concerns and their carbon footprint levels, and look to combine these patterns to provide networks that will produce some key simple building blocks safely and with the lowest possible carbon footprint. The Albert Mini CDT has a number of industrial partners, including AstraZeneca, Bayer, Cargill, Katsai, GSK, Johnson Matthey and Syngenta, and our first stage will involve modelling chemical processes suggested or endorsed by industry and identifying possible opportunities to further optimise these processes, bearing in mind that optimising for carbon footprint may look different to optimising for yield. Ultimately, the aim is to generalise the findings for chemical reaction networks for additional chemical processes. We will be building on well-established work in the chemical reaction network field, but bringing in a new, vitally important emphasis on sustainability. This interdisciplinary PhD will offer training in computer science and chemistry, and the successful applicant will benefit from industrial visits and a wide range of graduate training activities.
That's the end of this presentation. So I'll move on to the next one, which is actually myself. So bear in mind on me. Okay, so hopefully you can see the slides here. So this project is about verification of human-robot teamwork for chemical experiments. And for this project, you'll be supervised by myself, Pedro Ribeiro, lecturer in computer science, and my colleague, Dr. Jihong, who already talked before. He's from the School of Physics, Engineering and Technology and leads the Robot-Assisted Living Laboratory in the Institute for Safe Autonomy. So as a student, you'll be based in computer science, and you'll become a member of the RoboStar Center of Excellence in Software Engineering for Robotics. And you'll also have the opportunity to make use of the facilities of the Institute for Safe Autonomy for this research. So why this endeavor? Well, if we look at some of the state-of-the-art robotic systems in chemistry today, and some of which have already been mentioned by other colleagues, what do you notice? Well, they all operating behind an enclosure to some extent. Now, of course, this can also be for desired purposes if you have to have a controlled environment in terms of the gases, the temperature, and so on. But at the same time, it means that most likely while these robots are operating, there's no human interaction, right? So there's limited human interaction going on. But precisely, laboratory experiments require a high degree of human intervention currently, which limits throughput and presents also potential safety risks. And so robots really could assist in preparation of chemical experiments and handling chemicals post-reaction via human-robot interactions, such as handling unknown or potentially harmful substances, facilitating reaction solvent removal with evaporators. And there's some equipment on the right of this slide that displays such kind of a procedure. However, demonstrating that these interactions can be conducted safely and effectively is currently challenging. So some of the challenges about this project are to do with what are the mathematical models that are best suited to capture these human-robot interactions? How do we cope with variability amongst humans and adaptation as people use these systems? And core of this project is really how do we tailor formal verification techniques for this domain? So the objectives really are about, first of all, characterizing lab tasks that are suitable for human-robot interactions, modeling the scenarios for these tasks, and then developing and tailoring formal verification techniques for this domain. So you're looking at things like model checkers and theorem provers, and then evaluate the performance, the efficiency, and the safety of these collaborative experiments to understand in what ways are we actually benefiting from that work in a way that is efficient, safe, and so on. So potential methodology would be to characterize the laboratory tasks, first of all, so to conduct experiments and interactions with domain experts in the chemistry department and identify requirements for such a human-robot collaborative system. So this could be designing a system or adopting such a system suitable for these kind of tasks. And an example is the kind of robots that my colleague Jihong already mentioned. Then it'll be about identifying and modeling these scenarios and applying formal verification techniques using model checking and theorem proving. And then finally evaluating this human-robot collaborative system on scenarios of interest. So that's really it about this project. Feel free to contact me or Dr. Jihong to know more about our project. Further details will also be available on the Albert CDT page. Thank you. Okay, I would now like to move on to the next presentation. Poonam, please. We can see your screen, but you can't hear if you're speaking.
Mute myself. Hello everyone, I am Poonam Yadav. I am a lecturer in computer science department at University of York, and I'm proposing a PhD proposal on communication failure effects on human behavior in autonomous robotic laboratory environments. This is a joint project with Professor Alina Guino, who is an associate professor in Department of Psychology. So if we move further in this one, automatic or autonomous robotic laboratory environments are complex environments, you know that requires continuous time-critical communication among autonomous components such as mobile robots to perform independent tasks. In the best case scenario, we assume that these systems work as perfectly as they are designed, but in real-time world or in real systems, in worst case scenario, it is assumed that the communication failure of a single component may hold the entire system, compromising efficiency and safety of these systems. So in this proposal, we would like to explore the effect of these failures on human behavior, how human or lab technicians or any other assistants who are working in automating these experiments in human-robot interaction kind of environment, how these failures affect them psychologically, from a psychology point of view. So that's what we are looking to explore this kind of a research area in a little bit more depth in this one. So if we look at the research objective, there are 4 objectives being defined in this case. First one is to identify and categorize various types of communication uncertainties that may arise in advanced robotic laboratory environment. Here we will be looking from a different communication point of view. When I talk about communication, it means technical communication, whether it's a Wi-Fi signals or we are using a proprietary software based communication or any other communication. Second is to investigate the effect of communication uncertainty on the judgment and behavior of the lab technicians and assistants in the ARL environment. It will focus on recording human perceptions such as sound, image, attention, or emotions during interactions with robots in natural environments. This kind of understanding will help us to navigate how to make these kind of experiences more subjective, to understand factors contributing to the feeling of safety and confidence in the environment. And we are looking forward to use machine learning approaches for data processing and analysis. We have potentially very good these skills and tools in the department in computer science as well as in psychology. So if you are a psychology student or if you are a computer science student, this project will fit in both domains, and you're more than welcome to discuss more about what is your expertise are and what are the missing pieces in this whole project, which we can provide support. Finally, the objective of the project is to develop and evaluate strategy aimed at mitigating the negative effect of communication uncertainties on a human behavior in ARL environment. And I think this is a very exciting project, and I'm really looking forward to see students who are quite enthusiastic about this kind of research problem, which we can look from a different perspective. Thank you so much. You can reach out to me later or Professor Elena anytime. Thank you.
Thank you very much, Poonam. So we've come to the end of the talks on the projects themselves. We now have some time for questions, if there are any questions in the room. If there are no questions, then we'll be providing some concluding remarks. Okay, so you've heard a lot about different projects from our colleagues. This is a wrap-up. So the YorRobots Albert Center for Doctoral Training has 18 projects that are covering several aspects across multiple disciplines, such as chemistry, computer science, physics, engineering, mathematics, law, psychology, sociology, and so on. You can find the full list at the following URL. Excuse me. You can also scan the QR code to get access to this website. I need to emphasize that applications should be via the department of the lead project supervisor. And so for each of the projects, you'll find an apply button, and that will take you to the corresponding department's PhD or application page, where you can look at the information that they've got there and also start your application. So autonomous robotic systems for laboratory experiments really present immense potential for impactful research, cross-disciplinary research in lab automation. The timeline for applications, the deadline is on the 5th of January, 2024. And we hope to be making offer decisions to successful candidates by the 15th of February. And the idea is that candidates, successful candidates, will be starting their PhD in September 2024. So for general inquiries, we have a dedicated email address, albert-cdt@york.ac.uk, where one of my colleagues on the executive committee of the Albert CDT will be happy to point you to resources and the right people for any questions that you may have. So this is it from me. If there are no questions, are there any questions? I'll stop sharing. Okay. I don't see any questions.
Oh, sorry. Can you hear me?
Yeah, we can hear.
I got a question about the project's funding. So if I apply I think all of these projects are very interesting, and I'm thinking about the funding thing. Can you just I don't know how to say that. Like if I apply the I remember one like cancer fingerprint that like project. If I apply that, how much funding I can get, or what kind of fundings I can apply?
Anna?
Okay.
Sorry?
Thank you very much for your question, Xiaohui. The process at the University of York is in 2 steps. You need to choose a project or projects to apply for. And you apply to the department of the lead supervisor of that project, and you follow the directions of that department associated with the description of each of the projects in our homepage. You will have the information about who is the lead supervisor, what's the department, and therefore you know to which department to apply. So after the application, there will be a short listing process to be carried out by the potential supervisor that will require, if you are shortlisted, then will be required to attend an interview. After interview, then the potential supervisor will, together with colleagues and the university, will make a decision whether or not to offer you a position. This offer is independent of funding. The successful candidates will go to a second round of selection where then they will compete for funding. So the Albert Committee will then consider all the successful applicants who have been offered a position as a PhD student and then allocate the funding that is available to the Albert CDT. Does that answer your question?
Yeah, I see. That's very helpful. Thank you.
Pleasure.
Thank you, Anna. Are there any further questions?
All right.
Okay.
Thank you very much, Pedro, for organizing this, and thank you everyone this afternoon. Thank you.
Thank you very much.